Hello, everyone. Thanks for coming to...
Mic check. Can you guys hear us?
Can you hear us? Yeah? Good. Hello, everyone. Thanks for coming to our talk. My name is John Rodriguez.
Oh, and my name's BY.
And we're going to be talking about Dagger today. And who's familiar with dependency injection libraries here? Great. If you are not, that's okay too. There are some talks available by Jesse Wilson, Jake Wharton, and Gregory Kick talking about Dagger 1 and Dagger 2 respectively. So imagine on day one, your architect, your tech lead, whatever, decides it's time to move from Dagger 2 because it's the new hotness. Piece of cake, right? Just switch some dependencies in your Gradle file and boom, you're ready to go. Not surprisingly, just switching these dependencies won't work. So let's go over a hello world graph migration example to start. Here we have a classic Dagger module. We can tell it's a Dagger 1 module from the injects and adds 2 attributes, which are no longer present in Dagger 2. Let's focus on the injects attribute first. This attribute defines the entry points to the dependency graph, that is, the injectable classes whose dependencies are defined by this module's methods, or associated modules. This is a hint to Dagger, and it's important for compile time validation. At runtime, we can inject our entry point class with its dependency. In Dagger 2, the injects and adds 2 attributes go away. Since components define an implementation of the contract between the generated graph and its consumers, we add component methods to expose these dependencies. And finally, we can inject our dependency into our activity example. Great, piece of cake, straightforward. However, chances are your app has many modules that will compose with each other in, well, a modular fashion. Suppose, for example, that you have an app structure where every time you go to you navigate to a new screen, you're going to append to this object graph. As a result, you'll be creating multiple object graphs, and when you convert to Dagger 2, you'll be creating multiple components. Refactoring this on a feature branch can take days or even weeks, and keeping it up to date will be a nightmare. Believe me, this guy tried. Don't be this guy.
All right. So let's see. What can we do? If we can just migrate everything, just switch out and replace a few classes here and there, what can we do? How can we get Dagger 1 and Dagger 2 to cooperate and work together? So with Dagger 1, we had these annotations at provide, at inject, at module. Well, what if we were to use different annotations for Dagger 2 so that the Dagger 1 compiler focuses on Dagger 1 and the Dagger 2 compiler focuses on the Dagger 2 classes, and they don't mess with each other. So that's what we did. We introduced provides 2, inject 2, and module 2. This isn't an open source library. It's just like I hacked a Maven project together that would change the jar and recompile the classes, and it just worked. I was surprised, but it actually just worked.
Maven Shade, right? Was the
Maven Shade plugin is the name of the plugin. That's right. So let's go back to how we do things with Dagger 1, right? So we create an object graph from a module, and a module is a collection of bindings. Now, the idea in how we can migrate is we have this collection of bindings, and we're going to start taking some bindings out of the Dagger 1 modules and out of the Dagger 1 object graph and putting those into a Dagger 2 object graph and then tying these 2 graphs together. All right? So say we have this app module, which is Dagger 1. It has 2 provider methods, one that gives an OK HTTP client, and I just lost my mic, so I'm going to need a second here. Yeah, I don't know how to do it. Do you want to? Goodbye.
I don't have any jokes prepared. And no, I'm not going to dance salsa, even though you tweeted that.
John is a pro salsa dancer,
Yeah,
so I was expecting him to.
Yeah,
Thanks
that's the after party.
Thanks a lot. So let's
Back to
continue.
our regularly scheduled program.
So we have these OK HTTP clients and this retrofit client that are provided in the app module, right? And so we just create a new module at module 2 that uses Dagger, that's going to be in the Dagger 2 world, and we move this thing over, right? And so Now these dependencies are missing from the Dagger 1 graph, and they exist in the Dagger 2 graph. Now that's cool. Then we create a component with the add component annotation. We reference the module there, and we had this. And now we need to provide those two bindings back into the Dagger 1 graph, which means we need to expose them from the component so that they can be consumed. So that's why we have these component methods, which are equivalent to injects equal in Dagger 1. Cool, so we're exposing these things. That's great. But as we add more bindings, we're going to add more methods. And those aren't really there to stay. Ideally, once you finish the migration, you're done and you throw them away. So what we're going to do is we're going to create an interface that we're going to name app component facade, because I wanted to use a new design pattern name.
I was going to say, it sounds like a French design pattern. What's a facade?
I don't know what it is.
Okay.
But
Game of 4.
It sounded cool. So what we're going to do is we are going to actually create a subcomponent, which is like a subgraph, that's going to be responsible for exposing those bindings to the Dagger 1 graph. That way, when we're done with the migration, we can just remove the facade. All right. And so you just have to put add subcomponent on an interface and then add it as a method in the parent component. Cool. And then we have a facade. It's all about construction today. And we have a bridge module. And the bridge module is responsible for exposing those bindings that now live in the Dagger 2 world, exposing them back into Dagger 1. So the bridge module is a module that has access to the facade, and then is going to provide those bindings back to Dagger 1. Cool. So we also have the bridge module implement the facade. There's no runtime benefit aside from that. If you add something to the facade and forget to add it to the module, then it's going to not compile. It's going to throw a compile error. So that's a great way to make sure everything is in sync. Cool. So if we come back to our object graph, what we have now is we create a component, the Dagger 2 component. We get the facade from it, which is a subcomponent. And then we create a bridge from that wraps the facade, and then we pass the bridge to when we create the object graph. Cool. So let's come back to our Dagger 2 module. So you might say that's like a lot of stuff. We basically multiply the number of classes by 4 just to migrate. It's all temporary. And what's happening is that we are creating this intermediary like bindings, but the actual configuration is actually moving. So that's a good thing. Now the problem we have is, say we want to migrate Oki HTTP client into Dagger 2, right? But the problem is the Oki HTTP client dependency needs a hostname verifier. And my hostname verifier is actually still in Dagger 1, and I don't want to move it because that's too much work, and I don't understand host names, and someone else is going to fix that later. How do I do that? Well, we do the same, but the other way around. So we have our app module, and we expose the hostname verifier from the Dagger 1 graph. And then we create another bridge module. So I needed a new name, so it's going to be the Golden Gate module. And it exposes the hostname verifier to Dagger 2. And it basically, when you try to get it, it goes into the Dagger 1 object graph and returns it. You'll notice the set object graph method here instead of a constructor argument. The reason is the Dagger 1 graph depends on the Dagger 2 graph. Dagger 2 graph depends on the Dagger 1 graph. We can't create both of them at the same time. So we need to fake create one, then create the other from it, then create the cyclic dependency. It's great. So we have our module, we include the Golden Gate module, and then we come back to that code where all we have to do is create an instance of that Golden Gate module, create the component with it, and then once we created the object graph, set the graph on the Golden Gate module. All right. I think that's yours.
Mm-hmm. So, follow that so far? Piece of cake? No? You may wonder, do I really need to migrate at this point? Dagger 1 kind of worked fine. Let me just punt on Dagger 2 until I have the new app that I'm going to write and I can start from scratch. Can we wait for the next startup idea? Implement it then, side project.
You all know the answer. The answer is performance. Perf matters, right? We all know that it's, hashtag performance. That's hashtag. I learned that the other day. It's cool.
I feel like we offended some like random culture in the world.
Yep.
With that sign,
Okay, I didn't do anything. The thing is, we all know that performance is super important, and we're not going to talk about enums or
Fragnums
but
or yeah.
We're going to talk about performance.
So, a high level, right? Before Daggers came along, there was Juice. Juice was great. It was great, especially for server-side dependency injection. But when you brought it into a platform like Android, you started to see that reflection impose a huge penalty. So Dagger 1 came along and eliminated a lot of that reflection. Unfortunately, it didn't eliminate every bit of it, as you may already know through your own research. Dagger 2 claims that, and it's a valid claim, that it eliminates all reflection and therefore is faster at creating these object graphs. To understand why, let's take a peek into the Dagger 1 source. And that's what I just said. So we see here that Object Graph Plus is called to append a set of modules to the current graph. Earlier we mentioned that navigating to a new screen might introduce new objects with new dependencies. Plus is how we're able to do this. Before Dagger adds the modules to the parent graph, though, it has to perform a check that all the links, the bindings in the parent graph, have been resolved. Each binding is loaded via reflection when needed, and is then cached for future requests by the linker. But I guess to summarize is that the explicit calls to plus or validate would resolve all the remaining unresolved bindings in that current graph at once. And that can be expensive. In Gregory Kick's talk, he actually mentions how Google, one of Google's core services, creates a new subgraph per network request, and so reducing the cost of those linking bindings was very important. Dagger 2, he claims, reduced that cost by 13%. Another benefit to moving to Dagger 2 is stack trace readability. If you're in the weeds of your code day in, day out, you may come across a case where you have to look at a stack trace through a debugger, and readability can be tough with some of the ways that Dagger 1 generates those classes. An improvement in Dagger 2 is to generate the code that you would have generated yourself if you were writing it manually. That's a huge benefit. While Dagger 1 was better than the Juice days, Dagger 2 is clearly more readable. And lastly, because of Dagger 2's strict annotation processing, no incomplete graphs are allowed. You can validate, as a result, you can validate the complete graph in compilation time as opposed to deferring it in runtime because of incomplete graphs. Now, there are some trade-offs to that. For example, you may have liked the incomplete graph generation, but Dagger 2 just disallows that. You will instead get a compiler error if any bindings are invalid or incomplete. But that's not the reason why we migrated. Those are good reasons. For us, scoping was a huge benefit of moving to Dagger 2. So we work at Square. Square is a payments company. And so being able to handle transactions, have a cart of items that a merchant clicks in an items catalog and assembles a cart and then applies taxes and discounts, you're only going to have one transaction occurring at a time. So how can we do this? Well, we need a singleton. So let's slap on a singleton annotation. But what does making a singleton actually mean? Well, to answer this, again, let's dive into the Dagger 1 source. At the heart of the Dagger 1 object graph is a notion of a linker and a binding. What's a linker? Well, it's a map of some class, in this case our transaction handler, to a binding instance. Okay, so what's a binding? A binding is like a factory. It's generated by Dagger and has three important components. I shouldn't say component, that's an overloaded term. 3 parts. Whether it's a singleton, an abstract attach method which will enable you to gather all the bindings that your generic T object depends on, and then the abstract get method which will create instances of T. So great, that's the theory behind the binding class. Let's see what gets generated for our transaction handler example. So this is what we get. We see, true to form, the attached implementation gets the analytics and tax cache bindings. And our generated get implementation will create the transaction handler instance from those bindings. You'll notice that the generated binding also has a singleton of Boolean. But how does that singleton work? Well, Dagger will wrap that binding in a singleton binding and cache it so that subsequent requests for that object will return the same one. Again, typical gang of 4 pattern behind the singleton. Okay, so the object graph holds all the singletons in memory. But we don't need that instance anymore, right? So we can just recycle it. Well, the object graph holds a singleton in memory. And when we want to go to the printer screen, we no longer need this transaction handler. So we can get rid of that object graph. On the printer screen, we're going to need a printer handler. And it can't be held by the same object graph because it's been recycled. So we create a new object graph. Well, jump ahead quickly. That was weird, double tap. Debounce click listeners on this. So actually there is a hierarchy of object graphs. And the parent object graph can hold singletons with a longer lifetime. Because again, the higher up the object graph chain, you're probably getting closer to your application scope object. And anything that's held in that graph is going to be held for throughout the lifetime of the application. As you go further down, you reduce the lifetimes of your objects. So this is where we started transitioning into this term of scopes. Scopes have a name. Scopes will have an object graph associated with them. If you move from a screen to a new screen, you've added another scope to your scope hierarchy. And this scope will have a lifetime attached to it, which is the time that you're interacting on that screen. If you move away, if you hit the back button or basically navigate up from that screen, that lifetime is no longer, and all objects should be garbage collected. But singleton isn't quite representative of how we're using it. It's actually more of a scoped instance.
Thank you. Mm-hmm. All right, so I'm going to try to not say singleton for the rest of that talk, because if I say singleton is the gang of 4 pattern, I should say scoped instance. But I'm probably still going to say singleton because we've been using that word for years. And it's really hard to stop using it. But, so let's talk about, as we saw, so basically we said performance is better. It probably doesn't matter because it's not really impacting that much. However, for us, for our Android apps, however, what's really important about Dagger 2, and the key reason we're moving to Dagger 2, is scoping. So we have this singleton transaction handler, right? It's at singleton. Now the question is, you saw there were a bunch of scopes of object graph, right? The hierarchy. And the question is, in which scope does the transaction handler lives, right? My instinct say, well, that's going to be the transaction scope. It was on the slide, 2 pages away. And it probably is, but the reality is we don't know. Nobody knows. You have to look through the code to figure that out, and we'll see why in a minute. So let's say I have a transaction flow object or transaction whatever manager, and it needs the transaction handler, right? So it's a dependency on the transaction handler. And we have a view. Wow, a nice Android view that's created by Android, so not managed by the object graph, right? So the view has no idea how to get a transaction flow because it's not living in the Dagger world. So how does it get a transaction flow? Well, we declare the transaction flow as an inject on the transaction module. Then when we create the transaction graph, we have the app graph, we extend it, we create a transaction graph by adding definitions from the transaction module, which now makes the transaction flow object available from that graph. So then in the view, all we do is we get the graph and then we say graph of, give me the transaction flow, right? That's great. So we have the layout that gets the transaction flow that has a dependency on the transaction handler. Cool. Now we have a card presenter because again, we do payments and we add a bunch of stuff to a card and then we pay for that card, right? And so that card presenter also need a transaction handler. Now the thing is that we have a card view and the card view is in the transaction flow, but it's like a view in there somewhere. And so we have a card graph that extends the transaction graph and the card presenter lives in the card graph, and the view needs the card presenter, right? So it's kind of the same thing, but in a different graph. So to sum up, we have transaction graph that extends the app graph, and we have card graph that extends the transaction graph. And we have a module for each, and they both provide one provides the card presenter, one provides the transaction flow. Now, the interesting part is they both depend on transaction handler, which we've seen is a singleton. So we expect both of them to share that same singleton, right? Which means that this singleton is going to live in the upper scope because that's the one that's going to live longer, so it needs to be there. So the transaction scope. So how does that actually work? So we saw object graph. Object graph has a linker, and as we saw, a linker is essentially a map for a key to a factory, to a binding, right? So when you call get on an object graph, it's actually pretty simple. It asks the linker, hey, give me the factory, and for that key, it gets the factory and then creates an instance. All right. But now we have two graphs. We have the card graph and the transaction graph. And so if I'm in the card graph, before trying to get something, I'm going to ask my parent, hey, can you, do you have that transaction handler? So that's how it works, right? You actually, every object graph potentially has a parent graph. And if it does, it's going to ask it for the key. And if it doesn't find it, then it's going to ask its own linker. Now, how does linker work? So let's say that the parent graph of transaction graph, so the app graph, doesn't know about transaction handler. So it's going to say, nope, I can't do anything. So then transaction graph goes into its own linker. And we're asking for a key. So we have this map of keys to factories. What if there is no factory because we just loaded? So that's where things get a bit more interesting. If I can't find a factory, if I can't find a binding, then I'm going to load the generated class, the one with $inject adapter. That's when this happens. And you saw the Boolean, the Boolean singleton that's in there. That's where we basically look at that Boolean. And if that Boolean is true, we wrap that binding into a singleton binding that's going to keep the instance around. And then put it back in the map, return it. All right, so in terms of, and that was too fast. Really debouncing, really. So to sum up, we have this card graph, this transaction graph. And the graph, they all hold on to linkers, which hold on to bindings, which are essentially factories, are able to produce things. And so because both the transaction flow binding and the card presenter binding depend on the transaction handler binding, the transaction handler binding is going to live in the transaction graph, and the singleton is going to be in that scope. But what if I remove the dependency in transaction flow, right? What if I have transaction flow not depend on transaction handler anymore? What happens? So I just remove these two rows. So now transaction graph never actually needs the transaction handler singleton binding. Card screen graph is the one who needs it, so that's where the singleton is going to live. So if we take a moment to think about that, this means I removed the dependency in one class, or I added another dependency in another class, and all of a sudden that dependency lifetime and scope is going to change. So scoping is implicit when you use add singleton on a class, which means you have no idea what you're doing, and someone can break your code anytime in the future. It's really bad, which is why we drink. Yeah.
You may wonder why this bottle appears in our slides so many times, and it's really hard to make singleton interesting. So a quick Google search shows this to be the most prominent image, and we went with it. Didn't know it was a whiskey, actually.
Yep.
We'll have to try it sometime.
Yes. So essentially, when you put singleton on a class, it's pure luck. It's probably going to work, maybe not. And how do we fix that? So the first thing that you want to do is you're looking at a singleton class and you're like, well, so in which scope is this singleton living, right? You want to verify. It's hard to do. So if you want to do that in your code, you basically imagine the dependencies as a graph, right? We have the entry points. They have dependencies, which have dependencies. So if you have one of those which is a singleton, you have to walk back, find all the things that depend on that, go until you find some roots, all of the roots, actually all of the entry points, and then you look at the highest one, and that's going to be the scope of your singleton. In other words, it's crazy. So we started by building a runtime thing that would basically use reflection in our debug builds. So you ask, you type transaction handler, whatever, the thing you're looking for, and it's going to look at all your object graph and say, oh, it's actually in this scope. And so like the little star over there means asterisk, means, oh yeah, it's in the root flow scope. So we built that. That's very useful. It helps us a lot, but it's not great. There is actually a way with Dagger to enforce the scope in which a singleton will live, and that's by not using @singleton on any class, but instead using provider methods. So instead of using @inject and @singleton on your class, you create a provider method for that object, and now the object can only be created by this module. So if you create a graph with that module, then that's where the singleton will live. If you try to inject it in some other place where it's not which would normally change its scope, then you're going to get a compile error because Dagger is going to say, I don't know how to create that thing, and you're going to be very conscious about changing the scope of an object. All right, so that fixes it. But it's terrible. Who wants to write provider methods all the time? Like, it creates a ton of code. It's safe, but it's really sad. Which brings us to we might want to explain what this is. This is the Unicode for Dagger 2. There is a character, actually. Yeah, sorry?
U2021.
U2021, yes.
So this is where Dagger 2 helps. We see that in Dagger 1, we had the transaction handler singleton and a transaction module. Dagger 2 allows us to introduce scoping annotation. So you'll see here that the way we do so is we create an annotation and we slap on the scope annotation right there, and boom, we have a scoping annotation. We can then use this annotation to replace all the previous singleton annotation markings with this new annotation called single in transaction. For there, we will create a component that will replace the object graph. We mentioned this before, and we'll add the scoping annotation to that component. This ties the singleton and scope together, and is easy to figure out now. It's more readable, less prone to developer errors due to readability. If you're thinking of onboarding a new engineer, and that engineer has to look at the code base and figure out how everything's tied together, this can help tremendously, and it has already. And finally, we'll add that module to the component, as expected, and replace those injects with the interface method. Now you may wonder, well, so every time you need a new scope, you have to create one of these scoping annotations. That can quickly get out of hand, and you'd be right. Dagger 2 leverages annotation equality to make this easier. And so if we add a value field to this scoping annotation definition, we'll see that we can reuse it across any scope we want. Simply provide some class that defines the scope, up to you how to define that. And now you'll have a one annotation definition, but providing the scoping capability. And you'll see we, in this example, change it from a single in transaction annotation to just a general single in, providing it with the scope of the transaction component class. It's a bit of a mouthful. I just want to make sure I go through that slowly. One bonus is that we're now one-click navigation away from being able to tie from the scoped instance to the component. So IntelliJ Find usages, all the wonderful developer tools in IntelliJ or Android Studio that you're used to is available now with this. So great. We saw how to migrate one graph in a variety of ways. It was hard, right? This will take multiple iterations to finally kind of get an idea how you'll tie the Dagger 1 and Dagger 2 object graphs, apply the scaffolding, and in a piecemeal fashion, actually perform your migration. But that was just one graph. Imagine if you have a hierarchy of graphs. You can't migrate them all at once. For the reasons mentioned earlier, you'll have a feature branch out there for a while. We do know how to migrate one graph, though. We've shown that already. So suppose we migrate the root graph. We can create the Dagger 1 root graph that delegates to the Dagger 2 root graph as seen here through a proxy graph. Same as the partial graph idea, and we will empty the Dagger 1 root graph, and we can simply add children graphs to that Dagger 1 root graph as we see fit. But the main concept is we're providing this proxy to eventually whittle down the root graph that belongs to Dagger 1 and eventually decrease it to 0 and then remove all Dagger 1 references in your code base.
Cool. So that's great, but like if you go top to bottom, obviously there's less graphs at the top, more graphs at the bottom. So if you try to get a few engineers to do that work, they're gonna like be stomping on each other and be blocked one by another. What's actually better is if you could migrate any graph at any time when nobody's working on that part of the app. So let's say that we want to migrate a leaf graph, right? Say the card screen graph. It's a bit more tricky, but we can do that. So we would start by saying, well, same thing. We're going to have a component that matches to that graph, right? And we had injects. We had card presenter as an inject. So now we have card presenter as a method there, all right? So we add a module, the card screen module, yada, yada, yada. That's always the same, right? Now, this is the interesting part. So my card screen, it needs dependencies that are coming from a parent graph, right? And here, the parent graph is a Dagger 1 graph, and the child graph is a Dagger 2 graph, right? So how do we get these dependencies? Well, Dagger 2 has a notion of component dependencies, which can be interfaces. So it's basically you're saying, I'm going to construct this component, and I'm going to give you an implementation of that interface, and you're going to, and it's going to give me the things that I need. I don't know how they're made. I don't care. I just want them. And so this dependency interface is going to basically delegate to the parent object graph. How do you do that? You have two options. One, you just implement it, and as we saw with modules, you just delegate to it. So you implement every method, and then you do object graph that gets of that type. It works. It's a bit boring, and you don't want to repeat yourself. So option 2 is to use a Java proxy that implements that interface and then looks at the return type and calls the object graph with that. Now, you could say, well, that's reflection again, it's not fast, but again, when you're trying to get in one instance out of there, it doesn't really matter. So with that, so this is our current state there's a bit more at the bottom and at the top, but this is basically where we are right now. So we've migrated a lot of things, but we're not done yet, which means actually maybe this is a total mistake and no one should do it because we don't know the answer yet.
It's late now. We've been doing this since September and shipping register every 2 weeks.
Yes, well, since December.
Oh, did I say September?
Yeah,
Sorry, I meant December.
But yeah, we've had releases of our main app with Dagger 1 graphs and Dagger 2 graphs talking together. And you have to imagine, like, you're saying, you know, I want this dependency, and the Dagger 1 graph says, okay, cool, well, I need this other dependency. Oh, all right, see here, okay. And then this guy's like, oh, I need this dependency. Just cross, you know, it moves across the graph and then comes back, and then you have your thing. And it might be surprising, but everything works. We haven't had any crash related to that. We're about 50% in, but we've done the hardest part. Now it's like all of the, like one screen at a time kind of
to
work.
be mindful, this is while other work is happening. It's not like the app is
Yeah,
stopping.
it's like,
we've done flow upgrades, retrofit upgrades, all sorts of upgrades while this is happening. So as you could imagine, this can become unwieldy without some strict structure as we've outlined, or at least suggested as an outline in today's talk.
Yeah. Now, we know what's next. Food. We're all hungry, and this is the end of our talk. So,
thank you.
Well, thank you. Do you have time for questions? No, I don't think we do.
If you have time, if you have any questions, you can feel free to ask in the 2 minutes we have, or just talk to us at lunch.
We can talk at lunch or wherever.
Yeah, probably better to talk at lunch. We're hungry too.